In this video, we'll go over nuclear reaction focusing on beta decay. Nuclear reaction refers to the change of the nucleus because you have a very unstable atom. And that unstable atom is unstable because nucleus is unstable. So they'll go through some series of reaction in order to relieve the nucleus. For example, here is a nucleus over here, and this particular reaction will go through a change within the nucleus. This one, it happens to be a neutron changing into a proton. And as it's doing that, an electron, a light particle is coming out. So there was some kind of change within the nucleus for this reaction to occur. There are all these different types of nuclear reaction in order to relieve that instability of the nucleus. And the one we want to talk about is beta decay. So this is the beta decay. And the beta decay are generated by neutrons. So here's my neutron, that white spherical circle, breaking down into a proton. So now it became green, right? And then into a proton and some electron. It's not exactly an electron, but its electron-like particle has been split off from the neutron. We can denote this as an example like this. Here's carbon 14, and it has a proton number 6. Carbon has 6 protons, and then it's going through a beta decay. So this is a representation of the beta decay symbol. So that's coming out. So that right here, so I'm going to underline this, representing this image right here. Okay, so that's the beta coming out, and that's and then you'll see there is a change in the proton, so it actually increased in number of proton by 1, and so you see 7. The one above it, you'll see that it says E right here. That E is another way to represent beta decay. A lot of textbook uses it, so hence I have put it there. And also there is a -1 and 0. That's the same thing. Now the corner on this, in the corner of all of these three, that's your mass number. This is your mass number. All of these guys on the corner. Everything that's on the bottom, that's your atomic number, or that's your proton number. Or atomic number. Okay, erase this. Okay, now let's go a little bit more in details. So loss of 1 neutron, gain of 1 proton, and then a beta particle has been released as this process is happening. The beta particle is much like the electron because it has no mass, nor does it have, and its charge is negative, so hence much like the electron. This happens when there's too many neutrons and too little protons. So in other words, you can say the neutron to proton ratio, or N/Z, okay, that's what we refer to as, is kind of on the high side, or greater than 1. High. Or greater than 1. If you have too much neutron, there is a lot of instability, and also if you have too little proton, same thing, and they'll go through what is called the beta decay. All right, so let's go do some kind of problem based on what we learned so far. Here it says show radon 228 going through a beta decay. So beta decay refers to that beta sign, -1 and 0. The mass number on the reactant side and the mass number on the product side, the summation of it should equal out. Well, the mass number on the the reactant side, there's only radon, so that's 228. Mass number on the right side, or the product side, we got a 0, and we're going to have an element probably with 228, and that's because we want to equal out to total of 228. So we have 228 here. What about the proton number? Well, the proton number is 88 on this side. So the proton number on this side totality should be 88. So far we have -1, -1 plus. And so what needs to go here? 89. What that means is the element that needs to go here should have a proton number of 89. Look in your periodic table and see where 89 is, and then come back. You might have noticed it says actinium AC, okay? So having this actinium right here, 89, -1, gives me radon 88. Let's try the next one. So you try on this one. Show thorium-234 decaying and emitting a beta particle, and come back and check this video. Here is the key. So you see thorium, there's a beta decay, and then you're forming protactinium.